We're at the beginning of the academic program in the 24th Congress. It is my great pleasure to introduce Dario Braga from the University of Bologna to give his keynote lecture this morning. I believe he's going to talk about making crystals with a purpose. Dario was trained as a cluster chemist, and in the early 1990s he was part of a significant group of people who diverted their attention to the then fledgling subject of crystal engineering, and he started looking at intermolecular interactions, notably hydrogen bonds in organometallic compounds. In those days it was quite a great thing to even analyze a crystal structure in terms of intermolecular interactions, and in the course of this search he identified many new types of hydrogen bonds which were distinctive to metal atoms, metals as acceptors, for example, the MH group as a donor, things like that. And he's a researcher who is not scared at all. This lack of fear is very important in a good researcher. And I think sometime in the late 90s, the inorganic chemist became an organic chemist. And he started looking at, of all things, solid-solid reactions, grinding, co-grinding, this sort of thing, pharmaceutical compounds. It was in the 90s that I actually got to know him, and we worked together on some of these things. If I could have the slide, please. So, this is a photo of the two of us sometime a while ago. So both of us, I think, are looking better today than we did then. And yeah, it was in a nice place too. I think he remembers very well. And so we did a few things, and research was all like that in those days, just doing a few things. When we collaborated, we didn't have not 1 rupee or 1 lira of funding. It was lira in those days in Italy. So not 1 rupee of funding. And we wrote all those papers on hydrogen bonding, which I was telling yesterday that research is not business. Very important to remember that. Research is research. Better be research only. So we did all this stuff. No funding, no nothing, just because we like to do this work. Research should be like that. Dario has always been like that. That's why he's been able to change his topics so nicely. And then a lot of his recent work is still fundamental. It goes back to stuff in solid-state chemistry that went way back to the 50s, 60s. This co-grinding thing has not been understood. This crystals with a purpose business. Some of the people who are standing behind, there are still a few sitting places in the front. So if you just leave one for me, you can please fill up the rest. I told Dario 5 minutes ago that he's going to fill up this room. And so please come towards the front. There are definitely places here everywhere. No need to stand. And so crystals with a purpose. Yes, purpose, but what purpose? And do other people feel that it is a worthwhile purpose? There is some criticism in our crystal engineering subject, and people say that, you guys do some crystal structures, put some interactions, and then try to figure out why you've made this and what the purpose is. So you fit in the purpose at the very end and when you write your papers. No, I don't think so. I think many serious people like Dario have put the purpose first and then tried to make the crystal afterwards, which is the way it should be. So, without wasting too much time, Dario, it's my very great pleasure. This is the second time he is in Hyderabad and the third time he is in India, so he's really not that much of a stranger. and really looking forward to your lecture. And you will, of course, if you want 5 minutes worth questions, you have, 50 minutes then of speaking time, and then I'll give you a signal maybe 2 or 3 minutes before the speaking time is over. Professor Dario Braga.
Did I get the first slide? Okay. Okay. Well, good morning, everybody. Great pleasure to be here today. Great pleasure to be the first speaker of this lecture, and great pleasure to be introduced by my good old friend Gautam Desiraju. I'm very grateful to the organizing committee and Professor Desiraju, of course, for having given me this opportunity. I've been missing India for many years. The third time is nothing. You know, I would like to come every year. And this is also the reason why I start this lecture by looking at connections between Italy, Bologna, and my institute with India. You know, I come from the oldest university in the Western world, 930-something years, quite old. Chemistry is not that old, but still we are about to celebrate, I think, our 80th birthday, 90th, I'm not quite sure. But this is the picture of our Institute of Chemistry. Today is a department of chemistry. And if you see, standing on the staircase, on the entrance, you can hardly see it. You know, there is a yellow circle now there. Well, this person standing on the staircase is actually Raman. Raman visited the Chemistry Institute in 1959. And this is the first Raman instrument, which is now in the museum of our institute. So Professor Bonino, the man standing next to Raman, was a spectroscopist, and he invited in 1959 Raman to visit India, to visit Italy, Bologna. More recently, we had another delegation. So we had a meeting in a Dalton discussion in which we organized with the Royal Society of Chemistry in the year 2000. So this is, I retaliate with Gautam. This is a picture of that time, and you can also see a Kumar Birada, young Kumar Birada, also standing with us in Bologna. So that's for the India connection. And now let's see the connection with the crystallography. This quite ancient building, actually, I didn't know it myself. I've been working there for decades until a fellow professor told me that under the roof, there are symbols of chemistry that were put there at the time the building was actually constructed. And one of these symbols are crystals. So crystallography was one of the disciplines, one of the areas that were engraved, inscribed into the facade of the chemistry department. So that's for crystallography. Then let's move to the third connection, which is relevant for my talk today, and this is the name of Chamichan. Chamichan was a professor of photochemistry. He brought photochemistry to Bologna. This is the lecture hall of my department. Gautam certainly remembers that very well. And this is actually a picture taken this year at the meeting on crystal forms at Unibor, which we organized in June. But if you were bored and maybe looking at the ceiling, as people do sometimes, you would see this symbol, which is an old Mason symbol, apparently, and represents a sun shining surrounded by a snake. What the snake means, I don't know, but the sun shining had a very strong meaning for the chemistry department, and this is because there was no UV lamp at that time, and Professor Chamichan with Ziba was carrying out photochemistry experiments on the roof of the chemistry department. Well, today we have UV lamps, so that's why I decided to start the first part of my talk by connecting photochemistry to crystallography. The purpose in this case is to use light to make crystals react or to explore their properties. And this is something we've been busy doing over the past few years. Professor Marini and Professor Greppioni, they are interested in the subjects which I am describing in the slide. But I decided to, take a little portion of the work which we have done in connecting photochemistry to crystal engineering by telling you something about photoreactivity. Also, I've seen Len McGillivray entering the room, so I think this is also will be interesting for him to know. This is work done in collaboration with Fabrizia and Simone. Simone is the magician who decided to follow the steps of Gerhard Schmidt. This is also brings in the early days, the early mention of crystal engineering, the earliest association of engineering with solid-state chemistry. Gerhard Schmidt was investigating, as you all know, photoreactivity, photocyclization in the solid state, and he was the one who began to think in terms of controlling, understanding, playing with intermolecular interactions in order to achieve it, to achieve a goal, to do something. Forces responsible for stability or crystalline lattice of organic compounds, until we will be able to engineer crystal structures having intermolecular contact geometries appropriate for chemical reactions. He was interested in solid-state reactivity. Schmidt postulates were relatively simple, where reaction occurs with limited atomic molecular displacement, and then we have to have the saturations closer nearby, and so the limit was set by Schmidt at about 4.2 Ohmston in order to get a photocyclization upon shining UV light. These are not, beware, hard and fast rules. There have been ample demonstrations that you have reactivity. I mentioned Professor Kaup, for example, but also from Yotoda, who did a lot of solid-state reactivity with organic systems. They did not require such specific cutoff distance criteria, but nonetheless, it works pretty well as a predictive tool, and this is why we decided to explore by playing with hydrogen bonding on the one hand and ionic charges. You will see ionic charges coming up in my talk many times. So the basic idea was to make a salt of the aminocinamic acid and try to see what happened if we were shining UV light on these crystals. You see, a family of compounds were actually prepared, and the first one we characterized, this is a CanCom we reported at the end of last year, and the first one we prepared was sort of, say, unsurprising. So you get a chloride of the 4-aminocinamic acid salt, and then you have a single crystal to single crystal transformation in the photocyclization product. Fair enough. What was not so conventional was that we were able to follow stepwise the transformation. On the same crystal, one crystal, UV light, 30 minutes, diffraction data, UV light, 30 minutes, diffraction data, step by step. This is all the work by Simone D'Agostino, the magician I mentioned at the beginning. And this is how the unit cell parameters changed. And you can also see how the volume was constantly decreasing stepwise as the transformation took place from 0 to 100%. So that's quite an interesting experiment. Of course, the kinetics of this transition was slow enough to allow this type of a complicated experiment. But then where we started to have more fun, because with the sulfates, we were facing a very different situation. The sulfate had two independent cations in the unit cell, and the distance, the separation between the cations were one in agreement with Schmidt postulate, 3.5 angstrom, and one they were too far away. So what would happen here on attempting photocyclization? Well, the answer is very simple. You had 50% of your crystal that photocyclizes and 50% of your crystal that does not. So the resulting product is 50%, quantitatively 50% photocyclization product. And this is also an experiment that could be followed on the same single crystal, stepwise, through the reaction from beginning to end. Came last year. More recently, we decided to, wow, this is quite remarkable, fascinating results we are getting out. Let's see what we do with the bromide. Bromide was in the beginning relatively unsurprising, because the bromide, if you prepare the bromide in hot water, boiling water, which you get the compound which is isomorphous with the chloride. And being isomorphous with the chloride behaves well and photocyclizes to the photocyclization product, no problem. But you see, this compound is named form B, which is weird. You know, where is form A? Well, form A, which actually returned first, as you may guess, is what you get from at room temperature. And form A is a polymorph of form B. So then the question is, what's the relationship between form A and form B? Well, very simple. If you grind form A, you turn it into form B, and then you have a photocyclization. But how about shining UV light on form A? You know, this is the answer, the question is that you don't get any photocyclization. You activate a polymorphic transition. So form A turns into a form C, which does not photocyclizes, but then it's a different modification. So we were facing a very intriguing situation. Why the same material with distances between vinyl bonds which are very comparable, in one case does photocyclization and the other does not? Well, the answer is very naive for the time being. We have to investigate this further, but what we found is that in the form C, the cations are linked by the carboxylic ring. So the COO hydrogen bonded carboxylic ring. Form B does not possess the carboxylic ring. Form A and Form C do. So they do not cyclize. So is this a general rule? Is something specific of this compound? Well, interestingly, the nitrate, the tetrafluoroborate, and also the hexafluorophosphate do not undergo any phytocyclization, and they all contain the carboxylic ring. So our inference, it's an inference for the time being, is an observation, is that the energetic cost of breaking or deforming the carboxylic ring is too expensive, is too high, and then the photocyclization does not take place. Okay, that's the end of part one. Let's move to part two. In part two, as Gautam was mentioning before, I connect mechanical efforts, grinding with crystals. Well, this type of audience certainly can appreciate that grinding is not the best way to get crystals. You know, certainly not the best way to get single crystals on the machine. You smash crystals with grinding. But it's certainly a good way to explore the stability of crystal forms, and this is why we have been using this systematically through years to explore the crystal space, polymorphic modifications, hydrate formation, salt formation, co-crystal formations, and there is, we published a few papers on this. And I decided to get to a story, a little story, which is, I think is quite adequate for this type of audience, of a mechanically induced crystal form from crystals to solid solutions. All started with this lady. Well, we're in India here. I know the Christians here are about 5% in this area, so not everybody can recognize Santa Barbara. Santa Barbara is celebrated in Europe on the night. She is actually the saint patron of armorers, military engineers, gunsmiths, tunnelers, miners. Why do I mention Santa Barbara? Because it was on the night, December 4th, 1894, night of Santa Barbara, that Adolf von Bayer prepared barbituric acid and named the compound after the saint. Barbituric acid, it's a very interesting molecule. It's not a drug per se, as you may know. It's a precursor. It's a prodrug, which allows to prepare a wide variety of compounds which all have effect on consciousness, sleep, etc. Quite popular because this is a favorite drug for committing suicide, used to be at least, and there are many other applications of barbiturates. This is not the reason why I'm mentioning this compound to this audience, of course. It is because of the structural property relationship. Barbituric acid has many tautomeric forms, and we all know the ketonic form. If you go through Sigma Aldrich or any textbook or ChemSpider, Wikipedia, you always find barbituric acid represented as the keto form. This is quite right. As a matter of fact, this first structure determined by Jeffrey in 1961 of the dihydrated showed the barbituric acid in the keto form. Later on, the anhydrous form was determined by Bolton, again keto form. And the keto form is also the commercial form, which was actually characterized in 2004 by Lewis and Price. So everything converging keto form is the form of barbituric acid, including gas phase and solution. Fair enough. So you imagine that we were a little bit surprised while doing one of our grinding experiments. We found that we had obtained a very different powder diffraction pattern, which did not match any of the known crystal forms of barbituric acid, nor that of the hydrate. So it was a new form. But that, as I said, smashing crystal is not the best way to get a single crystal, so we were stuck with this powder. And our good friends and collaborators, historical collaborators in Turin, did the carbon-13 magic angle spinning, and we had a clue, an important clue. The CH2 resonances had disappeared, and we could clearly see one single resonance for a CH group, which was consistent with the presence of an enol form. But which one of the two tautomers? We had still an ambiguity. We had to disambiguate the structure between the monohole and the trihole. Well, it was not until we found a weighty collaboration with Jacob van der Streek. I saw him around. I don't know whether he's in this audience today. And also my good friend Martin Schmidt at the University of Frankfurt. We managed to collect high-quality diffraction data on powder and solve the structure of this new polymorph by powder diffraction data. And it turned out to be the monohole form, which was reported in Angewandte Chemie in 2011. Interestingly, because this is an audience that should appreciate this, in 2016, a new paper was reported, again in Angewandte Chemie, reporting the single crystal structure of a stable enol tautomer of barbituric acid. The authors correctly quoted our paper, referring it as the inference on the structure of the enol form. Well, of course, you may guess whether we had solved the structure, determined the structure, or inferred the structure. Never mind. doesn't matter. The important thing, the real reason why I mentioned this paper is why they could manage to get single crystals. And this is quite extraordinary. It should be a warning for everybody having forgotten vials or chemicals on a shelf. What they write is that they got the sample after 7 years. And in 7 years, they was checked by Raman, only 80% of the vial or the containing barbituric acid turned into the enol form. So a very, very slow kinetical transition towards the stable crystal form of barbituric acid. So our Walter Mercoon was right once again. It takes time. In this case, it took 140 years before getting the crystal structure of the stable form of barbituric acid. So that was all the beginning of a new story. Of course, once you know about barbituric acid, the next question was, how about thiobarbituric acid? Thiobarbituric acid is also isomorphous and has tautomeric forms. The structure of barbituric acid has been investigated much more thoroughly. I don't go into the details of these compounds for sake of time. The reason why I'm showing you this picture, is that you can see that some of all the structures are in the keto form, others are in the enol form, and there is a very complicated phase relationship between the polymorphs of thiobarbituric acid. I'm not getting into this. I only note that in our experiment, grinding experiment on thiobarbituric acid, when we did it in acetone, we obtained something which did not match any of the known powder diffraction patterns. Once again, apparently a new form. And this new form was so stable that form 6, which was the ketonic form, and form 3, which is also ketonic form, turned into this new form 4 with time. So we managed to get to grow single crystals of form 4 and saw the structure. And what we established is that the stable form of thiobarbituric acid is that of a co-crystal. It's a co-crystal of the keto and the enol form, crystallized together in the same lattice. So that's another nice crystallographic story. But then what's the purpose? How do we connect these two things? Here is where we get to the more recent stuff. Because recently we realized that by doing this type of research, we had gathered in family of compounds, and one form of barbituric acid was isomorphous with one form of thiobarbituric acid. So we were then in not the very stable forms, but they had two isomorphous crystals, and they were two isostructural almost isostructural molecules. So we were in the condition that Kitaj-Gorodsky had pointed out long before, that these two crystals could possibly form a solid solution, because putting one into the other would not perturb the structure too much, too extensively. Similis, similia solvuntur, if you allow me a little bit of Latin. And that's have a random distribution of one molecule into the lattice of the other one. This was reported in Kencom end of last year. And again, once again, you look for something, and you often find something else, and this something else sometimes even more interesting. Indeed, barbituric acid and thiobarbituric acid form solid solutions in the range 20% to 80%, but there is one singularity point. When we get to the one-to-one composition, 50% crystal, we end up with a crystal which melts 20 degrees above the crystal of thiobarbituric acid, and more than about 10 degrees above the melting temperature of barbituric acid. So this is a crystal which is, as a mixed crystal, is much more stable, at least in terms of melting, than the parent compounds. It was not a random distribution of molecules. It is actually an ordered array of molecules. They systematically arrange in the crystal to form a pair of molecules in which oxygen and sulfur face each other. You may see that the sulfur-sulfur combination on the right-hand side would be put the sulfur atoms too close together, oxygen-oxygen combination would put the oxygen atom too far away. So then oxygen having the ideal conditions for forming a regular ordered crystal structure. So this is actually a co-crystal. It's not a solid solution. It's a co-crystal of barbituric acid and thiobarbituric acid. This result was actually in agreement with a paper that recently published by Sally Price on the possibility of exchanging sulfur for oxygen in organic compounds when oxygen is not involved in hydrogen bonding. So then we get to the step further, which actually is a step back in terms of time, and not for the story I'm telling you. Serendipity is a major player in real life research. And this is a picture taken from my cell phone in 2009 of a slide that Professor Ulrich Grieser was showing at a meeting in Bologna. It was comparing the IR spectra of barbituric acid with in ground KBr or gently mixed with KBr. And you could see that there are stretching frequencies which appears in the ground compound. We have had some past experience with organometallic systems, so we decided to investigate this strange behavior on purpose. And so we made crystals on purpose of a stoichiometric combination of KBr and barbituric acid. And we did it also with sodium bromide and also with rubidium bromide. And we ended up with the classes of new compounds in which barbituric acid interacted both with the cation and with the bromide anions, forming isomorphous crystals of sodium, potassium, and rubidium bromide dihydrates. Well, cesium iodide, cesium bromide also forms compounds of this type. They have a different melting point, of course. They have different dissolution rates, properties that we can begin to perceive that we can tune properties by forming this type of aggregates. For this type of audience, it's also interesting maybe to know that these isomorphous sodium, potassium, and rubidium bromides turn into different crystals upon dehydration. So anisomorphous crystals, which then revert back if you add water back. So it's a reversible transition from isomorphicity to anisomorphicity. Very difficult word to say. Nevertheless, this allowed us to say we had discovered a new class of compounds. They were co-crystal. Yes, they were co-crystal. There were two types of materials into the same stuff, but then they were not organic molecules. They were not neutral molecules. They were crystals formed by an organic system and an inorganic salt. So we call them inorganic ionic co-crystals, and meaning hybrid materials in which you had a neutral molecule and an inorganic salt. Had we discovered anything real new? Well, not really. Not really. If you go to the database, you find several examples of this type of combination. But the interesting, in a way, is also more in the, say, in the food industry. Our good friend, Dr. Erling, came to Bologna at a meeting, and then he went back to Nestlé, and they started to systematically investigate the interaction of carbohydrates, sugars, with sodium chloride and ionic co-crystal. There is a nice Christensen.com highlight, and also this is a very recent paper. The structure of glucose sodium chloride has been investigated by many people. So anyway, this was a step, an important step towards innovation, from serendipity to innovation, because then we decided to pursue this matter together with people in drug companies. We were working with the UCB company in Belgium. They owned the piracetam molecule, which is the drug used in neuroscience, and also lithium chloride is still being used in neuroscience. So the idea, which was very simplistic, so how about putting together two neural drugs piracetam and lithium chloride. And indeed, you can form aggregates of piracetam and lithium chloride, hydrates and anhydrous, and also with lithium bromide. So this was in Kencom in 2012. And that's also opened up the investigation of a series of compounds. I'm not getting into this story because it is quite intricate. Just want to point out again, this is a crystallographic audience. One of the extravagant, weird aspects of this situation. If you have single crystals of the lithium chloride piracetam dihydrate, and you heat it at 1 centigrade per minute, you get a different outcome than if you do it at 5 degrees per minute. In one case, you melt the crystal and you have a melting point of the dihydrate. In the other case, if you go slow, you get go through the dehydration process, you get the anhydrous material, which then melts at the different temperatures. So you can get the lithium chloride anhydrous compound by slowly heating the dihydrate. So that's for our first step into ionic co-crystals with drugs. And then people at UCB said, well, why don't we try with other fellow molecules in this family? Brivaracetam, celetracetam, complicated names. So we set up to systematically explore these compounds. There are UCB patents on this, and indeed by changing the partner, using magnesium chloride or calcium chloride beside the alkali halides, and they all formed inorganic. They all formed ionic co-crystals. For some of these compounds, the interesting outcome was the intrinsic dissolution rate. For other systems, it was the thermal stability. But for some systems, it was crystal shape, morphology. Now, morphology is not a property which is really very interesting in academic labs. We all like to get nice crystals and maybe take a picture and report a picture of a nice crystals into a paper. But that's not clearly our main concern. But believe me, when you start interacting with drug companies, you realize that properties that are less relevant for us are might be much more relevant for them. So this is why they were very happy to see that by forming the ionic co-crystal with calcium chloride and magnesium chloride, they could get these crystals of this nice shape that allowed filtration and packaging in a much better way. So that's the end of part 2. And now we move to the third part. Third part brings in another hot topic of crystal engineering, namely chirality. We have been fiddling around with chirality for quite a time, and you might guess that with this exploring the interaction of organic molecules with inorganic salts, the idea of seeing what could happen in when a crystal of an organic molecule would interact with, of a chiral organic molecule, would interact with an inorganic system was quite a natural question. So we decided to set up an experiment in which we compared the behavior of enantiopure materials towards formation of ionic co-crystals with respect to racemic materials, to racemic crystals. So what would we expect? We had a big question mark. Probably nothing very serious. lithium chloride or sodium chloride or lithium bromide are certainly, definitely achiral. As you may go and look at the big crystal structure of sodium chloride in the main hole. So we were quite intrigued by the behavior of our system. This was reported in Crystal Growth and Design at the beginning of this year. We had a good master student, Lorenzo, who managed in a short time to prepare all the salts with lithium chloride, lithium bromide, and lithium iodide by using, on the one hand, L-histidine, and on the other hand, DL-histidine. As you can see from the slide, they all form hydrate compounds. And, we were not surprised with L-histidine to find that around the lithium cation, 3 L-histidine molecules had joined together, coordinating to lithium, and the fourth site on the tetrahedral coordination, let's call it coordination polyhedron about lithium, was filled with a water molecule. No. Well, this is quite a misleading picture because what really happens in the crystal is that we have a chain of lithium cations bridged together by the L-histidine molecules. The system clearly is chiral, and the crystal is chiral, and these chains are organized in the crystal lattice in parallel fashion, and you are seeing the projection down the axis of the chain we see on the top of the slide. Fair enough, nothing unexpected. What was slightly more unexpected was the behavior of the DL-histidine, the racemic crystal. We ended up with a racemic crystal, of course, so we started with a racemic crystal, but within the crystal, the lithium cation had exerted a chiral choice. They choose to have only one type of enantiomers, ending up in a system which had chains exactly of the same type as observed in the enantiopure material. And you see the overlap of the chains as in the DL and in the L crystal. So the DL-histidine compound contains chains, enantiopure chains with L and with D, separately joined, coordinated to lithium cations. All right, that was quite something, to ponder. Then we move to the lithium iodide ionic co-crystal with L-histidine, and natura non facit saltus. I cite Latin too much today. So we had the saltus because the DL product was actually superimposable. You see the diffraction pattern with the L compound. So we had obtained a conglomerate. What was the structure of the conglomerate? Kind of a Pasteur tartrate salt, you know? What was the structure of the conglomerate? Well, the conglomerate had exactly the features we expected. So they contained L-histidine on the one hand, crystals with L-histidine, and crystals with the DL-histidine on the other hand. They were identical in terms of symmetry, except for the chirality. So to sum up to this bit of the story, we have on the one hand the histidine with lithium chloride and lithium bromide, which behave in the same way, forming a racemic crystal, in which, however, the chains are enantiopure, and with lithium iodide, we have a conglomerate of L and D histidine. So the racemic crystal is a racemic crystal or is a kind of a co-crystal conglomerate, because we have separate structural units of opposite chirality. Question which is still open, and in order to pursue this matter a little further, and this is unpublished result, we decided with a student from Bulgaria to, in collaboration with Teresa Duarte at the University of Lisbon, to try a similar approach by seeing how general this behavior was, and move from histidine to proline. I sum up the story, not to bore you too much, but there are very strong similarities and very interesting differences between the two classes of compounds. Once again, lithium exerts a chiral preference for one chirality only. And with the difference between the two systems is that with proline, lithium chloride forms polymorphic, I don't know how to call them. From both type of crystals, you can get either the conglomerate or the racemic pseudo co-crystal conglomerate on the other hand. Lithium iodide forms the racemic crystals only, and lithium bromide so far has given us only the conglomerate. So certainly we are observing a strong chiral preference of tetrahedral coordination. I generalize to tetrahedral coordination, so you may now guess that we are exploring this type of approach also with transition metal atoms prone to tetrahedral coordination, as we are exploring the behavior of, say, intrinsically centrosymmetric structures as the octahedral coordination you may get with some alkaline earths or transition metals. So that's the end of the third part, and now wrapping up this talk. If you want to know more about our journey in crystal engineering land in Bologna, you may go and read this paper we published in UCRJ, which tells us a little bit of what we've done through the years. And I have a few personal remarks, which are personal, so I don't expect anybody to agree fully with me, and certainly not Gautam Desiraggio. Crystal engineering, and this is what he said at the beginning, has turned many crystallographers into crystal makers. I sometimes say that we were freed from the slavery of diffractometry. The time, I am old enough to remember the time of my crystallographers, going at chemical conferences and listening to interesting talks by people reporting results. He was mentioning metal cluster chemistry and acknowledging the contribution of my crystallographer. Then now we decided with crystal engineering to become our own masters and make our own compounds. Simple, naive, whatever, but this is our own story in where we use our own knowledge, our own perception of the factors that are important in the stability of a crystal, the way crystals transform, the way crystals behave. So now we are crystal makers. And the second point is that crystal engineering has no borders. We all agree with Gautam's holistic view of crystal engineering. Crystal engineering is across physical, organic, inorganic chemistry, but also has strong ramifications within nanomedicine, biology, pharmaceutical chemistry, materials chemistry, really connects, as crystallography does, by the way. Thinking of Tom Blandet's lecture yesterday, you know. This key feature of crystallography is embedded into crystal engineering, part of the crystal engineering philosophy and soul. One thing which is important for me, also my personal experience, is that crystal engineering has generated many new jobs opportunity. Awareness, sensitivity, commercial interest, whatever you want, but now pharmaceutical industry, food industry, cosmetic industries are now hiring people with the knowledge in solid-state chemistry and in techniques to characterize crystalline materials. And this is because of our work, or the work we have been doing, you know, increasing awareness, and which is good. It's good for the young generation. Third, actually, finally, the outcomes of many crystal engineering experiments are still far from being fully predictable and surprise-free. We don't want it to be so, because after all, maybe we are not so good in terms of, we are not so good engineers in terms of design, construction, utilizations, but certainly we like experiment, discovery, and have fun. This is why crystal engineering is true science. Thank you. Oh, well, stop. We don't walk alone in crystal engineering land. You need a brave heart company. This is the group in Bologna at the time in January. Fabrizia, Lucia, Simone, and some fellows from Bulgaria, Latvia, and Ukraine, and our students. And then the company, was generated in 12 years ago, and she's actually sponsoring my participation to the meeting, polycrystalline, which is now FDA approved, and you see a bunch of smiling young people. They have a job in chemistry and in solid-state chemistry, thanks to the work we had done in crystal engineering at the University of Bologna. And I thank you all for your attention.
How forming the co-crystals of active pharmaceutical ingredients with ionic salts affects solubility and bioavailability of these crystals, of these materials. And the second very specific question is about the racemic resolution of amino acids with lithium halides. Did you also try fluoride?
Okay, the first question is, well, these compounds are prepared, in terms of preparation, they are prepared usually by mechanical grinding. In terms of properties, we systematically explore the solubility and intrinsic dissolution rates. The general rule is that you increase the solubility in water, of course, and also the intrinsic dissolution rate by factors, okay, which is good. Then you have to be aware of the parachute effect. You know, once the thing is in solution, after a while, you see the usual trend. The solubility of the drug is reestablished in half an hour, 1 hour, 2 hours, depending on the system. But certainly we get a high, we can bring in solution a large quantity of the organic drug. An effect we have noticed recently on the system, which I did not speak about today, in co-crystals, ionic co-crystal with cyanuric acid, which are also very interesting in using in swimming pools, for example, cyanuric acid, is the effect on sodium chloride, because this is also a way to decrease solubility of sodium chloride. Rather, you increase the solubility of the organic material, but then since the inorganic salt is complex in the solid, the solubility of the alkali halide decreases, which is in some cases also an interesting effect to keep in mind. What was the second question? You had the second. Oh, no, we never tried fluoride.
Yes, please.
Yeah, thanks for the nice talk. My question is, for co-crystallization, is it always necessary that the co-crystal will have higher solubility than the drug, or can lead to a low solubility material on co-crystallization?
Well, yeah, if this is a general question about co-crystals, then the answer is it depends. Usually, whenever you trap the organic molecule in interactions in the solid, it also happens with hydrates, for example. Okay, then you can decrease the solubility. Depends on the solvent. Of course, we're talking about water. Hydrate is less soluble. When you have say barbituric acid, for example, the solubility of barbituric acid is lower than the pure organic material. But it's not, once again, it's not a hard and fast rule. There is not a systematic rule. It depends on the balance between solvation energy, once you get to deal with the real solvent, water, and the interaction energy in the lattice. So we have seen different behaviors depending on the system.
Yes, please.
First of all, thanks for the nice talk about co-crystals. I wanted to ask you if one of the main problems of pharmaceutical is the control of the production of the enantiomers when you have chiral. Did you try, or do you are using this ionic crystal system to control enantiomers productions in some pharmaceuticals? Because it could be a very interesting way to do things in pharmaceuticals. They could look at it very carefully, I mean.
Yeah, thank you. This is a very useful suggestion. As I said, this is quite a beginning of a new line of research. So what I told you are very recent results, which you can open up in all directions, and the one you indicate is certainly worth pursuing. We are in connection with a drug company I cannot name at the moment. We are planning some well-thought experiment. I might be able to say something more maybe next IUCR meeting.
Hello, yes.
Thank you, Dario, for presenting an excellent overview from the Bologna kaleidoscope for crystal engineering. Your last comment that making crystals can also create new job opportunities, I just thought I'll mention that on Saturday there is a special session, micro symposium. How does crystallography help in your career? And that could be useful for many of the younger and even not so younger colleagues who are present here. So just thought I'll highlight this point since you made it in your concluding points. Yeah, thank you.
Yes, please, right there in the middle.
My question is in the chirality domain. Normally, when you take a racemic system, you will end up getting a racemic crystal. But there are cases they will spontaneously dissolve. We would like to know about your thoughts on why in some systems they will resolve and they will just separate it out during the crystallization, but while in most of the system they will tend to form a racemic crystal.
Well, can you say that again?
In some of the systems, normally, the system tends to resolve spontaneously. They undergo spontaneous resolution of the system. But, most of the time, the racemic crystal would always get into a racemic space groups. And so we would like to know your personal thoughts on why in some cases it would occur. What is the driving force for a system?
I cannot answer this question. I have no idea. As I said a minute ago, this is our preliminary observation. Take it as for what it's worth. On forming ionic crystals with lithium, we see a clear chiral preference for one enantiomer only. I've tried to model arranging both enantiomers around a tetrahedral by keeping the distance, in a reasonable distant way, and apparently you can. So nothing would. But the magic number 3, having 3 molecules around the tetrahedron, in the fourth site is not available because the steric intensity will be too much. Apparently suggests that the 3 molecules of the same chirality around one of the faces of the tetrahedron is much better than molecules of different chirality. But this is the beginning. We have to explore the systems much more in a much broader way before coming to any conclusion. I cannot answer now. I'm sorry.
If you have a short question, because I have a comment myself, which will be the last one. Yes.
Do you have ideas how to prepare a nice what are the conditions to prepare a nice big single crystals of ionic co-crystals? Yeah. What are the conditions to grow a big single crystal?
A big single crystal.
Yeah, for these ionic co-crystals.
No, they are very well behaving. You can imagine. These systems crystallize very, very well. So the condition for growing a big crystal are the usual tricks for growing a big crystal. So it takes time, slow evaporation techniques. Once the system is done, what we do sometimes is to encourage the crystal to form by seeding, by using a powder from the grinding original starting material, after checking with the powder, the fraction, of course, whether it is a pure material, to start seeding the solution and let it slowly crystallize. But some of these materials go to very, very large, very nice behaving crystals. Yeah. I forgot to say, with some of these materials, also NLO properties are of interest. But we have not explored these so far.
See, I had a comment because nobody asked the speaker any question about the final comments that he made. And I believe Dario has laid down some very important things here for all of us today. And also we are in a meeting of the IUCR. He has used the word crystallography a few times. And in this community there is considerable amount of debate about this crystallography word, chemistry word, crystal engineering. The union itself has wrestled with this problem. And we have commissions. Most of you don't know about the commissions and there's no need to know. Yes. But we have this commission. It used to be called Commission for Small Molecules. And then in 1996, it changed the name to Commission for Structural Chemistry or something. A lot of voting and all sorts of things, debates. So it got changed, the name got changed, and what does this mean? And we had a meeting of the Journal Management Board 2 days ago. This thing keeps coming up because all of us have, why publish in ACTA? What is ACTA B? It's meant for crystallography, not for chemistry. This kind of nonsense talk goes on all the time. ACTA C, nobody wants to publish there. IUCRJ, he has mentioned. This is a meeting of the IUCR, and so I want to talk about these journals and our subject in this connection. And I made the statement that there's no point in troubling ourselves with old words, because in science, sometimes the old words lose their meaning and they have to be dumped. So this word called chemical crystallography, I made the statement that there is no subject called chemical crystallography anymore. If anybody here can define it, please, I would like to know. So what is this chemical crystallography? It used to be a very famous word in, say, the 50s or 60s, something like that. Then came this other word, structural chemistry. What is structural chemistry? To me, is meaningless. All chemistry is to some extent or the other structural. So what is the structural chemistry? And then Dario has used this word, this crystal engineering. I forgot to say, or I didn't have the time to say, that he was the founding scientific editor of Crysteng.com. So the journal was confident enough to have the name crystal engineering in its very title, and Dario has spearheaded all these things 20 years ago. And in many senses, I would hasten to add that instead of all the subjects where crystallography and chemistry are coming together, gradually have come under this umbrella word called crystal engineering now. And in this, I would say that the subject of metal organic frameworks comes very much into this framework. So these old words like chemical crystallography, structural chemistry, am I a chemist, am I a crystallographer, all these things really don't have much meaning today. And so I would try to give some confidence to the younger people in this audience, because all of you will have discussions with your colleagues and things like that. What are you doing? I'm a physical chemist, I'm an organic chemist, etc., etc. Crystal engineering, what's that? So yeah, it's It's a real subject in its own right, and I think Dario's lecture has pointed out so clearly to all of us, maybe to some extent preaching to the converted, but I think in a more general sense, this subject of crystal engineering, where he has played such an important role, has truly come of age by the time of the 2017 Congress. Thank you, Dario, once again, for your most wonderful lecture.
So it's my pleasant duty on behalf of LOC. I would like to give a small gift to the speaker. Dario, please come. Yep. Yes. And a small gift to our chairman.